In this video, we're going to cover circular motion. It's important to understand circular motion. It's in quite a few places. I mean, it can be like in this merry-go-round at the park. You see an example of circular motion. You know, a loop-de-loop at an amusement park, or even like satellites orbiting Earth are all examples of circular motion. And we're gonna start by looking at an example of like a roundabout or a traffic circle. So let's say we have this bus and it is traveling at a constant speed around a traffic circle. Okay, so as this bus goes around, the white arrow is representing its velocity vector. You'll notice that the magnitude or the length of that vector is not changing. So that means that it is traveling at a constant speed. Okay, when that is the case, that something is traveling in a circle at a constant speed, okay, now its velocity is changing because its direction is changing, but the magnitude of the velocity is not changing, so its speed stays the same. That's a special case that we call uniform circular motion. Okay, so there's a definition. Uniform circular motion, like I just said, is motion around a circle at a constant speed. So for there to be uniform circular motion, the object does not have to complete the circle. So like if you're going around the roundabout and you travel at a constant speed, but you get out before going all the way around, which is typical, right? For a small section of that, you could have traveled in uniform circular motion. Okay, so right here, as you go around like a quarter circle, this part of the motion we can analyze with uniform circular motion. Okay, after that, it appears to be just linear motion like we've analyzed in the past. Okay, or you could go halfway around or 3/4 of the way around, or even just keep going on and on, around and around the traffic circle. Okay, so let's take a look at this a little bit closer. So if we have an object whose velocity is changing, so the magnitude of the velocity is staying the same, it has the same speed as it goes around the circle, but the velocity is actually changing because the direction of that vector is changing as you go around the circle. Okay, so the object actually is accelerating, and the object is accelerating in a direction that has to be perpendicular. Okay, so perpendicular to this tangential velocity. So this velocity is tangent to the curve, or tangent to the circle. So if we had any component of that acceleration along this line that's tangent to the curve, you're going to have the object either speeding up or slowing down. And since in this case it's always kind of turning to the left, it makes sense that your acceleration vector is going to be pointed to the center of the circle. Okay, it's not going to be pointed out here because it's turning to the left kind of the whole time. So that acceleration is pointed to the center of the circle. You'll see that I have a subscript C there. That's because we have a special name for this acceleration. It's called the centripetal acceleration. Okay, centripetal means like towards the center. Okay, so when we look at this centripetal acceleration, we've already said that it points towards the center of the circular path. Okay, it's perpendicular to the instantaneous motion, or perpendicular to this velocity. Okay, and it changes the object's direction, not its speed, when we're looking at uniform circular motion, because the speed stays the same, and the acceleration is causing the direction of the motion to change. Okay, but what is the magnitude of this acceleration? Well, I'm going to do something that I don't really want to do, but I'm just going to give you the equation. So our centripetal acceleration equals the velocity squared divided by the radius. Okay, so the linear velocity, or the speed, the magnitude of the linear velocity, which is the speed. So the speed of the object squared divided by the radius of the circle. Okay, so from the path around the circle to the midpoint of the circle, or the center of the circle. Okay, so that's our equation for centripetal acceleration. And we'll do an example, or I'll have a video with examples that you can watch after this one. But basically, just kind of plug and chug. If you have uniform circular motion, you know your velocity is not changing, and you're asked to find that centripetal acceleration, take the magnitude of the velocity, square it, divide by the radius, and that's your acceleration. And it's pointed directly towards the center of the circle. Okay. If something is accelerating, though, we know that acceleration is caused by a force. So there's got to be some force that is causing this. Let's go back to our example of a car going around a roundabout, or a bus moving around a roundabout, or traffic circle. There's got to be some force that is causing this to accelerate, causing its velocity to change direction. And oops, I went the wrong direction. And we call that a centripetal force, and it's directed along the line. It's pointed towards the center of the circle again, because that's the direction of the acceleration. So we call the acceleration, or the force that causes the centripetal acceleration, we call that the centripetal force. Okay, and it's directed towards the center of the object's circular path, similar to the acceleration. Okay, this can be caused by many different types of forces. So in this case, where we're looking at this this bus going around the traffic circle, the friction between the tires and the road, that reaction force is what's basically going to change the velocity vector, change the direction of this velocity vector. Okay. We could have a tension force, like in this swing ride that you may have been on or seen at a fair. Okay, here is a tension force. There's a component of this tension force pointed towards the center of this circle that these people are going around on these swings. Okay, so it could be a tension force that is producing that centripetal acceleration, or that centripetal force. Okay, or we could even have, if you've been to a racetrack, or even like when you get off a freeway, sometimes you'll see that the road is banked. So it can even be a normal force. In a banked road, you have actually a component of that normal force that's pointed towards the center of the circle. So even if maybe the friction between the road and the tires is bad, if you're not going too fast, a normal force can provide that centripetal force to keep that object going in a circle, on a circular path. Okay, so regardless of the type of force, we can call all of these a centripetal force if it's directed towards the center of a circle in a circular path that an object is taking. Okay, but how do we calculate the magnitude of this force? Okay, well, if you recall, Newton's second law says the sum of the forces are a net force acting on an object equals its mass times its acceleration. Okay, well, if we're looking for the centripetal force, let's put a subscript c, and that equals the mass times the centripetal acceleration. Okay, in uniform circular motion, the acceleration is just that centripetal acceleration. So if we plug in our v squared over r, we get that centripetal force equals mv squared over r. Okay, so this tells us that the force, the centripetal force, the force required to keep an object in uniform circular motion, is directly proportional to the mass and the speed squared, and inversely proportional to the radius of the circle. Okay, so we can actually take a look at this. So we have Mary McNary here, and I've strapped her into some terrible carnival ride. Okay, so let's go ahead and move her in a circle. So in this case, the tension in this string is going to be what's producing that centripetal force that keeps her going in a circle. So let's see if I can do this, not hit myself in the face. Okay, so I can kind of feel, and you could do this at home if you have a setup kind of similar to this. So I can actually kind of feel the tension force. And so let's see, so I'm kind of constant here, and then let's see if I speed it up. I can feel that tension force increase, that centripetal force, or that force directed towards the center of the circle, because the string is kind of like pulling back on me. So you can actually kind of feel it increase. Okay, and now if I were to spin her at like the same tangential speed or linear speed, but increase the length of the string to increase the radius, okay, she's moving pretty fast, maybe about, I'm trying to make it about the same, but like the actual force that I feel in the string, or the centripetal force, the tension force, is way less. Okay? And then I could also increase the mass. I'm not going to do that because then it'll be hard for me to get her actually up and spinning. But you can do this little fun example at home if you would like. So our centripetal force, again, these variables are the mass of the object. Oops, I gotta make myself small again. Okay, the mass of the object is what the m stands for. The v squared over r is the same as before. V is the speed, and r is the radius. Okay, so as kind of a review of what we talked about so far, we have in uniform circular motion, so when the speed of the object is not changing as it traverses that circular path, the centripetal acceleration equals v squared over r, and the centripetal force is mv squared over r. Okay, so those are kind of the two key takeaway equations from this video. I do here at the end want to talk about non-uniform circular motion for a minute. So what would happen if we have a velocity that is changing throughout its as it travels this circular path? Okay, so here we see the velocity decreases between here and here. The magnitude of the velocity and the direction of the velocity is changing. Okay, its magnitude decreases, and then its magnitude increases, and then increases a little more, and then it decreases. So we have a changing magnitude of velocity. Okay, so if we were to draw out the acceleration vectors and plot and put those on our diagram, okay, they would look something like this. Okay, and if we split that overall acceleration vector into its components that are parallel and perpendicular to this tangent line right here that just touches the edge of the circle, then we actually get a component AC, that's the centripetal component of the acceleration, and we get a tangential component, AT, and this tangential component right here is going to work to either increase or decrease the speed, and this centripetal component is keeping this traveling in a circular path. Okay, so even if this acceleration, even if we have a changing velocity, we still have a component of this acceleration that is the centripetal acceleration. Okay, so I could go around and draw those two components, the perpendicular and parallel to this tangent line at this point for all of these, and we get acceleration, a centripetal acceleration pointed to the center that's a component of this overall acceleration vector, instantaneous acceleration of the object at that point. Okay, so if we go through, we could think about, okay, we're looking at this tangential acceleration in relationship to the velocity. Well, it's pointing in the opposite direction here, so the speed of this object is decreasing, and that makes sense when we look at the next one. It's shorter. It is kind of a ways, but it's a shorter length. That white velocity vector was shorter. Okay, here we have the velocity vector and that tangential acceleration, which is working to speed up the object because it's pointed in the same direction as the velocity. Okay, and then remember this is the overall acceleration vector, and it has a component that's keeping it in circular motion here. This centripetal acceleration component. Okay, we look at the next one. They're also in the same direction, so again, its speed is increasing. Okay, but then the next one here, its speed is going to be decreasing because the acceleration is pointing the opposite direction of the velocity vector. Okay, so that's just an example of the fact that you still have a component of the acceleration that's a centripetal acceleration, even if it's non-uniform circular motion. Okay, so hopefully this video was helpful. I think you definitely want to watch the next video where I go through a couple examples, but that is circular motion.